Alright, this is the introduction for the lab on latent heat, and what we're essentially going to be doing in this lab is we'll be measuring the latent heat of fusion and latent heat of vaporization for water. One thing I'll mention is the measurement for latent heat of vaporization of water is not spectacular, and you're going to be shooting for an order of magnitude rather than like trying to hit this one exactly. That one is just very difficult to measure. Don't forget to answer this question and this question. Please do that ahead of time, but just don't forget them. Now what we're going to do is we're going to essentially be using the same setup that we used last time. The setup that we used last time looked kind of like this. I didn't mention the white bucket in the picture, but this white bucket's going to have some ice in it. We're going to use the same research grade calorimeter. You're going to use a beaker and graduated cylinder for your water transportation and heating up the water, as well as the measurement of the water. Again, please use the graduated cylinder for measuring the quantities of water. You're going to use a temperature probe as you did last time, and we are not going to have this metal sample. I was just kind of efficient with my picture taking. I hopefully don't forget to get these guys out, but for some reason I always seem to, and you're going to use these guys that are shoulder height all around the room. So what we're essentially going to do is we're going to take a look at water going through a phase change. Have a nice little simulation for the first part of this experiment right here. Essentially what we're going to do is we're going to get some ice, and don't remember exactly how much ice you're going to get. It's going to be a little bit. And this ice is going to essentially start off at 0 degrees Celsius, or so we're going to assume. Then what we're going to do is we're going to get ourselves some water, and you're going to get I think 100 grams of water. I'm just going to put 50 in right here, and it's probably going to be sitting around room temperature. Then what's going to happen is we're going to go ahead and dump that ice into the water, and what's going to happen is you're probably going to see the temperature of the water go down, and eventually equalize. Now, what you're going to do is you're going to measure the final temperature of the system, and more or less what we're going to say is the heat that was gained by the ice more or less came from the water. So let's go ahead and work our way through the lab here. You're going to measure the mass of the calorimeter just like you did last time. You're going to dump about 200 milliliters of warm-ish water into it. Warm-ish is room temperature. The exact temperature doesn't really matter too awful much, and you can subtract the two, get the mass of the water. You can stick the temperature probe in there and measure the initial temperature. One thing that is super important is to make sure that you set your logger probe to go for a relatively long time. Now when you dump the ice in, this is going to happen in hopefully less than 30 seconds, but I do have this in there twice because when you come to the second part of this lab, if you forgot to set this thing to 30 minutes, then there's no way to recreate it, and we need to start from fresh. You're going to grab yourself a couple of pieces of ice. I don't really have tongs, just scoop it out. And when I say a couple of pieces, I mean don't grab one piece, but don't grab like a big old handful. You're going to go ahead and dump that into your research grade calorimeter, and you are going to make sure that you stir this. Stirring is very, very, very important. Once the ice has completely melted, then you're going to record the final temperature. Now this may take 10 seconds, it may take 30 seconds. If it takes like 5 minutes, then you got too much ice. You want to make sure that it melts, and it melts relatively quickly because we are losing heat to the room throughout this entire process. What you're then going to do is you're going to measure the mass of the whole kit and caboodle, subtract the previous measurement of mass with this one, and you're going to have how much ice. Where did the heat from the ice came from? Well, it probably came from the water. We can go ahead and calculate what this is. More or less what we're going to do is we're going to say Q is equal to mass of the water, specific heat of water, we know what that is, and the change in temperature of the water. When the ice melted, how much ice water did it produce, and what was the temperature of this ice water? I don't know about you, but this thing had darn well better be 0 degrees Celsius or nearly. Then what we can do is we can say what we had this melted ice water that was living at 0 degrees Celsius, and it ended up at the final temperature. So what we can do is we can say this is going to be the heat that it takes to warm up the ice water. That's going to be the mass of the ice, the specific heat of water, and the change in temperature of the ice water that is again going from 0 degrees up to the final temperature. If this is what was available to it, then what you can do is you can subtract this guy off and say the remaining heat had to be the heat that went into melting the ice. So you can then go ahead and say, well, I know the heat that it took to melt the ice. That's going to be the heat to melt the ice is going to be the mass of the ice and the latent heat of fusion. If I were to take the difference and divide by the mass of the ice, then I can calculate my latent heat of fusion. Compare that to what we expect and what were the main sources of error in this experiment. Then what we're going to do is we're going to measure the latent heat of vaporization for water. So you're going to get that glass beaker, and you're going to start with it empty, and you're going to measure its mass. Please, please, please don't use the calorimeter here. I have had people that have tried to do this, and we're going to set this thing on the hot plate, and that's probably not good. So you're going to put about 100 milliliters of water into the beaker, measure the mass, essentially tear it out, stick the temperature probe in there, and measure the temperature probe. Before you put the beaker on the heater, turn it on, crank it to full. Do not mess with that temperature probe, and wait a couple of minutes for everything to kind of reach equilibrium. While you're doing this, make sure, very, very, very important, that the software is set to record for about 30 minutes. If you forget this step, there is no going back. You need to go back and redo everything. Then what you're going to do is you're going to go ahead and set the beaker with the temperature probe in it on the hot plate and give it some stir. Please, please, please stir as it does this, and be very, very, very careful of the wire on the temperature probe. What you should see is we should see the temperature go up as the time goes on. So it should go on there, be sitting there, sitting there, sitting there. It's going to go up, and then it's going to hit the magic number of 100 degrees Celsius, and it's going to start to boil. Now we're going to use the two pieces of this of the graph independently. And what you're going to do is you're going to say, I know what this time was, and I know what this change in temperature was. So what we can do is we can calculate the power rating of this heater. Now this thing right here does say 300 seconds. There's a really good chance that this is going to be less than 300 seconds. More or less, I got the I got some new heaters, and these new heaters are relatively spectacular. So this time is probably going to be less than 300 seconds, but use this time right there. From this change in temperature, what we can do is we can say Q is equal to MC delta T, and if I were to say the power rating of this heater is going to be the heat over time, I can go ahead and I can calculate this thing. So what you're going to do is you're going to use this piece of the puzzle just right there. Then what we're going to do is we're going to use the boil time, and when it comes to the boil time, I say go ahead and let this thing boil for 5 minutes. So now we're talking about this time right over there, and what we can do is we can say the heat added to the water. Well, essentially that's going to be the power rating of the heater multiplied by the time that we boiled this thing for. This is why we want to not mess around with the temperature probes, because we don't want to mess around with the temperature or with the power rating of this heater. Now with these newer heaters, they do heat up faster, but I suspect they cycle on and off, but that doesn't seem to impact this lab too much. What you are not going to do is you're not going to be taking the temperature probe in and out a whole awful lot in this process, because every time you take this thing out, you're going to lose a little bit of water. What you're then going to do is you're going to measure what's left over from this guy, and then we can say, well, how much was vaporized. If you take the difference of the final to the initial, that's going to be how much was vaporized. And then we can go ahead and we can calculate the latent heat of vaporization for water. Compare it with the value of in the textbook. The percent error is going to be relatively large. I do know this. We're only going to vaporize like maybe 10 grams of water or so, and we tend to lose quite a bit of water just with sloppage in this particular lab. So for this guy right there, the percent error will be large, but we are shooting more for like a order of magnitude for this guy.